Okay, now we come to the AC network analysis, right? Earlier we learned about the network analysis, but most of the circuit is DC source, right? Even both voltage and current source, right? So it's in DC. But how about AC network? The AC circuit is the circuit that have some periodic signal of voltage and current, and sometimes it's come uh, mostly it's come in sinusoid waveform, sinusoidal waveform or sine and cosine. Okay, in sine and cosine form. Okay, this is signal when uh, the time or we have time and signal voltage or current. Okay, we have amplitude and periodic and frequency of this signal. Okay. So in this part, we'll be in the AC network analysis and AC power. I will talk about power here, right? But not all the section in the chapter 4 and chapter 7, not every section, okay? Just some section. Okay, let's see. Before we talk about AC network analysis, first we will discuss about the source, right? Time-dependent source. AC is the source that change its amplitude during the time, as it usually come in periodic signal. And we know about the energy storage device here, which is the capacitor and inductor, right? Capacitance and inductance. Okay, and then we will solve the circuit using phasor solution. Phasor solution is the method that we solve the time domain into vector form. We solve it in vector form, which is easier to solve the circuit, right? And then in vector form, you need to use your knowledge on complex number. Okay, complex number. Okay, complex number, you have real and imaginary part, right? Okay, if you have forgot something, you can remind how to add, how to multiply complex number, and how to divide a complex number, how to write down in polar form and complex form. V and theta, or maybe R plus Jx like this. Okay, this is a complex form. This is polar form, right? You have 100 with 30 degrees. How to transform into complex form, right? Real and imaginary part, right? Okay. It's familiar with you. This is, do you remember? Okay, I think many subjects may use this, right? Some subject will use complex. So, okay. So for energy storage device like a capacitor and inductor, right, in the circuit, it will respond, as we say, respond to the voltage and current in change only. If the voltage is constant and the current is constant, this device will not respond. It means that the capacitor will act at open circuit and the inductance will act like short circuit element in DC. Okay, right? In DC. This is open circuit and this is short circuit. Open and short. In steady state DC, steady state. Steady state means the circuit has been in that condition for a long time. Nothing changed, no switching, nothing changed to the circuit. In steady state, DC circuit. But if something changed, it will respond to that change for capacitor and inductor like this. So this device will act only when the circuit have some changing. Changing sometimes we say transient state, right? Transient state. If something change, we call transient state. And AC circuit. Okay, this kind of device is charge and discharge energy, right? Charge and discharge energy. If nothing change, it just fully charged and there is no discharge at all. Okay, or it's just fully discharged and then act. No response to the circuit. No response to the circuit. Okay. But if the circuit is changed, like AC circuit, this element will respond to the circuit. Okay. Okay, for ideal capacitor, the capacitor will respond to the circuit by this equation. The current flow through the capacitor or capacitance will corresponding to the change of voltage. Okay, if the voltage is changed, the current is there. If the voltage is not changed, if the current across the capacitor is constant, there is no current flow. Nothing changed. Okay, nothing changes means current is zero. Okay, and it's depending on one the parameter called capacitance, and we use C for that parameter capacitance here. Okay, so I equal C dV by dt is the property of the capacitance. Okay, here. I will not go into detail about to analyze this because it's, if I touch on the tangent analysis, we need to solve this type of equation. Okay, but in this case, we will simplify in phasor form later. Okay, just know the its characteristic. So it will act to the system only when voltage is changed. And in AC circuit, what happened? AC circuit, the voltage change all the time, right? Okay, the voltage change all the time. Then the current will change all the time either, right? The current is that it's not zero. Okay. Here, if we connect the capacitance together, right? It can be in the form. If the capacitance in series form, we can use the formula of resistance in parallel, right? To get the total capacitance. If it connect in parallel, we just add up the capacitance together. Okay. You learn about this in physics, right? Okay, I think some in physics, right? Okay, let's see some response of the capacitor. If we have the capacitor and we supply the voltage like this, the voltage increase in this form. It means we supply voltage in this form. Okay. Here is the function represent this voltage. Okay, we slightly increase the voltage, right, in exponential form, and it will saturate at 5 volt. Okay, at 5 volt. Then after 5 volt, nothing change at almost constant voltage. Okay, almost constant voltage. Then see what happened, and the current is and the capacitance is 0.1 microfarad. Okay. Okay. If the voltage across capacitance is Vt, the current I would be I is C dV by dt, right? And what is the derivative of this function d by dt? D by dt into phi 1 minus e minus t 10 by 10 power minus 6 here. Can you differentiate function, right, by dt, right? Exponential and t. So c dv by dt, just make the derivative. This value is become 10 power minus 7 phi over 10 power minus 6 e power minus t by 10 power minus 6. Then we get, this is the current, right? By this equation, this is the voltage and the current flow will be in this form. What happens if we apply voltage, this voltage into capacitance? First, the current is very high. It's decreased from 5. This is the exponential with decay, right? It decreased from 5. Then when the time pass, it's decreased to 0. You can see it's corresponding to the voltage. If the voltage change very high, the current is high. If the voltage change not very high, the current is become lower, right? It's corresponding to the slope of the voltage, right? And when nothing change, the current is 0. Okay? The voltage not change, the current is 0. It's not, even the voltage is there. Finally, the voltage almost constant to 5, right? Almost constant to 5 volt. But the current, no current flow. Okay? No current flow. It means that the capacitance is just fully charged to 5 volt. If we disconnect the voltage, it will store 5 volt in the terminal. Okay? If you touch the capacitance, that time it will short you. Will start you some small power. Okay? You can try in the laboratory. Right? Just fully charge the capacitor and then place it on the table, right? And your friend don't know it's already fully charged, right? Okay, it have the voltage, right? And some capacitor have a very high volt, maybe more than 10 volt, for example. Okay, this type of capacitor. Sometimes this type of capacitor is a big one. The glass side here. Okay. Okay. Let's see another example. If you apply the voltage in this form, to the capacitor, what happened? At the beginning, the voltage is constant. The voltage constant, nothing change, right? D by dt is 0, right? So the current is 0. You can see the current is 0. Okay, and when the voltage change, the voltage is changed by this slope, right? Slope is dv by dt, right? The slope is 4 something. The current is there. If the voltage is not changed now, even it's already applied to the capacitance by 15 volt right here, right? But constant, the current not flow because it's just fully charged already. Okay, nothing, no current at all, right? But it's already stored energy in the capacitance. This means that the charge is already full on the positive and negative side. The charge is full, so no current flow. Okay. When you remove the voltage, is now can supply 15 volt for a while, okay, until it's discharged off. Okay, this is the property of capacitor. Okay, similar, if you have the current like this, it means no current is zero, the voltage is also zero. If the current is there, it means the voltage is become changed like this, right? It's slope of the voltage. Current is slope of the voltage, right? Here, multiply with the uh, capacitance value, and no current, no voltage change, right? Just like that, okay? So don't worry about this. So I will not talk about this complicated yet, because it's uh, when you when you would like to solve the when you solve the differential equation, you can solve by integrate both sides. Okay, you can write down in this form, right? Uh, dv would be 1 over c I dt, and then you integrate both sides. Okay, you will get the solution, right? The solution of v when you know I. Okay, in this case, when you know v, you can get I by differential, right? But if you know I, you solve differential equation, right? You integrate both sides of the equation. Still remember differential equation, how to solve ordinary differential. If you need to solve this type of circuit, you need to use differential equation knowledge. Okay, differential equation knowledge. Okay. Here, this is an example of the capacitance value of different capacitor. Okay, just for information. Okay, and the energy storage in the capacitor will be in this formula. Okay, with this formula. Okay, similarly for inductor, the inductance is act in the opposite, like in the opposite concept with the capacitor. The inductor will provide the voltage only when the current change. Only when the current change. If you have the coil, the magnetic coil, uh, I think you have ever do some experiment, right? If we have one coil, and then I place the magnetic, it's just the just place it, and nothing moving, nothing move, no moving. There is no voltage, right? But if you move this magnetic, the voltage will be happen, okay, will be take place, right? Similar, if the current change, the voltage is there for the coil. If the current is not changed, there is no voltage, okay? Just in the opposite way of capacitor, okay? This is, we call this inductor. The voltage across the inductor take place only when the current change, okay? If the current constant, for example, I equal to 10 amp constant, no voltage, okay? Because it's not changed, it's, we replace the inductance by short circuit because no voltage, okay? In steady state circuit, okay? Here. If we sum the inductance together, we'll use the same formula with resistance. Okay, the same formula with resistance in series form, in parallel form. Okay, and this is some example. I will go a bit fast. Just look to the graph. It's okay. Let's see this graph. If we supply the current to the inductance by this function. So first, no current. Then we start increase current with this slope, and the current is constant. First, no current, no voltage. Okay, the voltage across the inductance will be zero, right? When the current change increase in positive, right? In positive slope, the voltage is there, right? By this equation, right? And then the current just constant, no change for the current. The current is constant. The voltage is zero during this period, right? 5 to 10 is zero, right? Then the current decrease. The slope is negative, right? The voltage is negative, right? Because di by dt is negative value. Then we get negative value. Until the current not change, if the current not change, voltage is zero. Just like that. Okay, this is the response to the circuit. How inductance and capacitance respond to the circuit. It's just if something change, it's just respond. If nothing change, it's steady. Okay. Okay, I think I will stop here because maybe it's already 6 o'clock, right? No class after this class? No? Okay. Sometimes if we cannot